the maximum conduction band electron concentration would be around 10 to the 18 per centimeter cube. So that is also much smaller than the valence band electron concentration, orders of magnitude. So you can assume as if the valence band electron concentration is not affected at all, okay, by either doping or whatever. So thermal, how many electrons from valence band move to the conduction band? That depends on the temperature, because temperature determines the thermal energy of valence band electrons, and also the valence band electron density. Now you are saying that the valence band electron density doesn't change. So therefore the effectively doesn't change. So therefore generation rate is G, okay, which tells me how many electrons per centimeter cube would get into conduction band from valence band per unit time. So electrons moving from valence band to conduction band per unit time or per second, you can say, okay, per second per centimeter cube of volume. Okay, so this is what we are calling generation rate. So now that generation rate should be constant at a given temperature. If you increase the temperature, thermal energy is increased, and the generation rate should also increase. Okay, so since the generation rate, generation rate is so since the generation rate is constant, now you have a certain number of electrons coming up here. So, and you have some vacancies here, some hole here, like that. So these electrons now also recombine with the hole. This we'll do in more detail later. But these electrons also would recombine with the hole. So recombination. What would be the rate of that recombination? Now that if the electrons in the conduction band increase by a certain value, suppose they double in concentration, then the rate at which they recombine also would double, because there is a probability that this electron would recombine with a hole that or vacancy that it is seeing in the valence band. It would go to the vacancy, recombine with the vacancy. So this is just energy space. It's not in real space. This electron and this vacancy are together at the same place. In energy, in energy they are separated, not in the space. So this electron would recombine with the vacancy. There is a certain probability, because the electrons are spread over in that 1 centimeter cube volume uniformly, conduction band electrons, and the holes or vacancies are also spread over uniformly in the 1 centimeter cube volume. Therefore, there is a certain probability with which an electron would recombine with the holes. So that probability would then, because that there is a probability, so electrons recombination with holes, that rate of recombination would be, if you increase the electron concentration by twice with a given probability, so electron concentration, so one electron has a probability of recombination. Okay. So now with that probability, if the electron concentration is increased, suppose there are n electrons, that they would probably that they would recombine. Let us call this probability as P, or not P. Let us call it PR, something like that. Okay. So then, in that case, if for n electrons, the rate of the how many of them, so there is a probability that this electron would recombine in 1 second, that is PR. Now if there are n electrons in 1 second, how many would recombine? N into Pr, isn't it? And now one electron, so likewise, if there are one electron, suppose it has a probability that it would recombine with one hole with the probability Pr within 1 second. So n electrons would have a probability of n Pr. Now suppose there are p holes, then this probability would be so n into p Pr. Isn't that would be the probability with which it would recombine the electrons, n electrons would recombine with p holes, okay, with n into p into Pr, that probability per second. Okay, per second. So single electron would recombine with a single hole with a probability say Pr, okay, within 1 second. So if there are n electrons, with they would recombine with a single hole with within 1 second with a rate n-Pr, isn't it? Likewise, n electrons with with p number of holes within 1 second, what is the rate at which they would recombine? It would be n into p into Pr. That's so. What I mean to say is that this law of mass action that we had seen here yesterday has a so that here yesterday we had seen it from Maxwell-Boltzmann distribution, but it is more fundamental. You don't need Maxwell-Boltzmann distribution. You can get it from more fundamental arguments as we have done here. Okay, so that's why n into p is now a constant. Okay, and in intrinsic semiconductor we know that n and p are equal. So therefore, this is actually Ni square Pr is a constant, and Pr is a probability that a hole would and a single electron would recombine with a single hole within a unit time. So now, since electrons and holes are uniformly distributed, therefore that's again a constant. Therefore, Ni square itself is a constant. Okay. So that is the fundamental argument behind this law of mass action. So you need not go through formulae. You can make this fundamental argument for law of mass action, and based on that you can say that Ni square is a constant. So at a given temperature. Now for intrinsic semiconductor it is Ni square. So what we are saying is that this is the rate of recombination. But when thermal equilibrium is there, in that case, this rate of recombination should be equal to rate of generation. Otherwise, there will be holes being generated or electrons being generated, both of would result in non-equilibrium condition. So, the rate of generation is equal to rate of recombination. And rate of recombination we said is this Ni square into Pr. So, this rate of generation should also be equal to Ni square into Pr. So, and then we make another argument that else is getting, I'm selecting something and something else is getting selected. Okay, it's fine. So rate of generation is equal to rate of recombination in thermal equilibrium. and this is Ni square into Pr. So this we said rate of recombination is Ni square into Pr. We said it is we said for intrinsic semiconductor. That's how we had discussed here. But suppose it's an extrinsic semiconductor. Would rate of generation change even if it is an extrinsic semiconductor? What is rate of generation dependent on? We said that rate of generation is dependent on the electron temperature and number of electrons in valence band. So at a given temperature, this is almost unaffected even for extrinsic semiconductor, isn't? This is similar for the number of electrons in valence band is almost unaffected by doping. Why? Because with doping, the conduction band electron concentration would increase to maximum 10 to the power 18 per centimeter cube. But valence band electron concentration is of the order of atomic density, which is 10 to the power 22 per centimeter of that order. So it's a orders of magnitude difference. So this doping would not affect the valence band electron concentration. So rate of generation we said is dependent only on the thermal energy, which is randomly assigned to all the electrons, and on the so at a given temperature, thermal energy which is randomly assigned to all the electrons is similar, and it won't change, and the electron concentration in valence band. So that's what rate of generation is dependent on. So rate of generation is just this. It would not change with whether it's doped or not doped, whether it's extrinsic or intrinsic. So if rate of, but in thermal equilibrium, we know that rate of recombination should be equal to rate of generation. And since rate of generation doesn't change for doped semiconductors, rate of recombination also doesn't change. Okay. So therefore, R is equal to this Ni square Pr for extrinsic, for intrinsic, as well as extrinsic semiconductor. So what do you mean by this? You mean to say that this law of mass action is valid for doped as well as undoped, in the sense intrinsic as well as extrinsic semiconductors, and that argument we have made from very fundamental arguments. This proposition we are making from very fundamental arguments. So is this something which was covered, or I am redoing it, Dr. Menka? So if I am redoing, you please tell me. Otherwise, I'll. So now the overall charge neutrality is maintained here, even in extrinsic semiconductor, the charge or intrinsic, whatever, overall charge neutrality is maintained. So that's how we write it this way. Okay. So what is this N here? What is the value of N? So, and what is the value of P naught? So we know that this law of mass action is valid. So Nd plus P naught. P naught is Ni square by N. Okay, is equal to N. So what it means is that you can write it this way: N square minus Nd plus minus Ni square is 0. So you can write it this way, and therefore you can get the value of N as you can get the value of N as roots of this, isn't it? So that then N becomes N Nd plus square root of Nd plus square plus N4 Ni square by 2. So in case whenever Nd plus is much larger than Ni, if you find that Nd plus is much larger than Ni, so if doping density is much larger than intrinsic carrier density, then N is nearly equal to Nd plus. Okay, that's what you observe from here. So because this minus is not valid, minus is the minus sign here is not valid, because if minus sign is valid, then N will become negative. So that is not valid. It's not a valid solution. Okay. So when we say that electron concentration is equal to dopant concentration, that is true for cases where the dopant concentration is much larger than the intrinsic concentration. Dopant concentration is closer to intrinsic concentration, then electron concentration is not equal to dopant concentration, but it should be given by this this expression.
To hear you.
Yeah. I'm just doing some figures. These figures I'm removing from here. I'm trying to manage that. Otherwise, so I was.
Sir, screen is also not visible.
Yeah. What has happened?
Screen is also not visible, sir.
Yeah. So there was some problem. It hanged, and that's why I'm managing that. There was some. It got hanged. So that's why. But whatever I am doing, have you done that in the previous sessions, or this I am doing freshly?
Sir, the charge neutrality and the mass section I have covered.
So this I should not do?
Yes, sir. You can skip this, but whatever was covered, that was actually I have not.
So this charge law of mass action from this basic probability arguments, that did you do?
Sorry, sir, I can't hear.
Charge neutrality from basic probability arguments, that did you do that? This,
no.
Which I did.
Then I have not done. I have taken that simple equation Np is equal to Ni square, and from there minority carriers, majority carriers, I approximated that N is equal to Nd instead of using the. So
right.
that thing I have covered because that was needed in diode.
Okay, so yeah, so this general expression that how okay, I should share it again, I think, isn't? Yeah.
Yes.
So this general expression that how the charge I mean, if the intrinsic carrier concentration and the minority and the dopant concentration are close, then what is how do you manage all that? Was it done or I did it again?
No, sir. Whatever you have covered, it is fine.
Okay, then it's fine. So I'm trying to do these things because I wherever you find that I'm redoing things that are done, so please tell me. Any one of you can tell.
Sir. Yes, sir.
Any one of you can tell. Okay. So I'm just doing this because these things are usually I think not covered in colleges in general, isn't it? So that's why I'm doing this. So right. So now let us look at an extrinsic semiconductor or N-type silicon. So which is at room temperature it is doped. Suppose. What would happen when you increase the temperature? So when you increase the temperature, it becomes again like a intrinsic semiconductor. Now it starts acquiring the nature of intrinsic silicon. Was that done in the class previously in this course? So otherwise, I will briefly do it. Suppose you have. So just now we have seen this expression, is it? Right. So suppose you are discussing for silicon how the concentration N would vary with temperature. Suppose this is an extrinsic semiconductor. So if you are discussing 1000 by T, so instead of T, the x-axis is 1000 by T. In that case, what is the expression that we have? Yesterday we had seen that expression, natural logarithm of Ni or is this. Okay, so it varies with temperature as 1 by T. A change is equal to change in is proportional to change in 1 by T, or in other words 1000 by T. Okay, so that should be a linear relationship. So if it is extrinsic semiconductor, we know that at room temperature, where this 1000 by T would be around 3, isn't it? That is what it would be. So 2, 4, 6, 8. So you will have somewhere here 1000 by T. Okay. So this is extrinsic semiconductor. Suppose it has a doping density of 10 to the power 16 per centimeter cube. So at room temperature, you have a constant near room temperature. You have a constant doping density, isn't it? And that is your ND. But at very small temperatures, what would be the doping density? So there you would observe that all the dopants are not ionized. I think you might have done this, that if you draw the band diagram, induction band, the dopant the electrons would get excited into the not valence band, this donor level electron. Professor Menaka, was this done, or is this these kind of things have not been done?
No, sir. It was not done. It was not done in detail. I just told the formula.
Yeah. So wherever you find that I'm repeating things, you please inform me. You or any of the attendants can also.
Yes.
Any of the people who are attendees can also inform. Okay, I'll just skip that part. Okay. So that's why at room temperature you find that all the entire ND. So what is this number corresponding to? This, if you see, this would be having a concentration of Nd. All the dopant ions would be contributing these electrons, and their energy level is very close to the conduction. Okay, because they are not tightly bound. So now, when at room temperature, because the energy difference between the conduction band and this donor level, this is called donor level, donor energy level. It's so close that at room temperature, kT by kT, 0.026 electron volt, is also it's also very close to the, so in the room thermal energy is usually 3 kT. So 3 times this 0.026 electron volt. So thermal energy is larger than this difference between conduction band and donor level energy, and therefore all the donor ions all the donor electrons are excited to the conduction band. So all of them are present in the conduction band at room temperature. That's why we say that at room temperature Nd is equal to N. Okay. So, and if Nd is much larger than Ni square, in that case Nd is anyway close to N. But at lower temperature, what would happen? At lower temperature, suppose the temperature is 10 Kelvin. If the temperature is so low, 10 Kelvin, what is kT by Q? kT. So at 10 Kelvin, you will observe that kT is so 0.026 divided by 3, that is 0.009 divided by another 10, 0.0009 electron volt. Okay. Now 3 times this is 0.01001 0.0027 electron volt. Now that is much smaller than the energy difference between donor level and conduction band. So you will observe that most of the donor level electrons are not excited to conduction band, but they remain trapped within the donor level. Is this fine? So you observe that doping density is now not, the electron density is now much smaller than the dopant concentration. So in such a case, you would say that electron density is equal to the ionized dopant concentration. So that's why we are writing this Nd plus instead of N. Nd, we are writing N is equal to Nd plus. So it is ionized dopant concentration. So you would observe that it is actually at very low temperatures. At very low temperatures, you will observe that it will, at very low temperatures means not here, but here, yeah. So at very low temperatures, you will observe that it is again falling, the concentration. That is because and it is equal to Nd plus. And it's not Nd, but it's Nd plus. And when Nd plus comes very close to Ni square, it's not even Nd plus, it is given by this formula. Okay. So at even lower temperatures, it is Nd plus square root of Nd plus 4 Ni square divided by 2, like that. Where Ni square is also a function of temperature. Ni is also a function of temperature. Okay, that. So that's how it becomes a very, so it's not so simple. Then you have to know all these things to get a value there. You know? But at very high temperatures, which is here, what would happen? Something interesting happens there also. At very value of Ni. So so you have this expression which we had derived yesterday. So, and in this, what is the dependence of NC and NB? What is the dependence of EG and NC and NB? NB. So that we had written yesterday. So based just looking at that, we would say that NC and NB, NC into NB would be proportional to temperature to the power 3. Is it? KT and you would also see that what is the, so therefore here, and what is the dependence here? Here it is EG. So EG, how is the energy gap dependent on temperature? The energy gap also has a minor dependence on temperature. So in the first place, if we just ignore that, in that case, you would say that this, even if you ignore that, you will say that with temperature, so this is a natural logarithm, within natural logarithm you have this KT. So therefore it's a weak dependence. This is the dependence which would dominate. So as you increase temperature, the value of, and this would keep on reducing, and value of Ni would therefore on the log scale increase linearly. So Ni would now, so how would Ni actually behave? So Ni would, if we plot with another color, suppose I plot Ni like this, the Ni would be behaving like this. Okay, that's it. Because that's a linear relationship, log Ni. With 1000 by T. Okay, so you can also write this as 1000 by T into Eg by 2000 K. I mean, you can write it this way, sir. So that's what you are doing. So with 1000 by T, and then log Ni would now behave linear. And this is Nd is now, all the electrons are now ionized. So therefore, how would the concentration Nd vary? So you can just see that. all the ions are now ionized. So these two would now add. So here we would observe that both the intrinsic concentration and the dopant related electrons would add, and therefore you would find that this would increase, and because the value of Ni is exponentially increasing with 1000 by T, you would observe that soon it is Ni which would dominate and Nd would not dominate. So at high temperatures, you observe that the silicon has become like intrinsic again, and dopants have no value at very high temperature. Okay, so at very low temperature, dopant ionization is incomplete, and therefore the dopant density is low, or electron concentration or carrier concentration is low. At very high temperature, because the intrinsic carrier concentration is now very large, it increases exponentially with 1 by T, and therefore you would observe that electron concentration is now dominated by intrinsic concentration, and it's almost like an intrinsic silicon. In the intermediate temperature ranges, that is where complete ionization of dopant ions has happened, and intrinsic concentration is also very small compared to the dopant concentration. So that is where you can assume that the electron concentration is, or carrier concentration is equal to dopant concentration. So Professor Menaka, I will give you a 5-minute break here. Hello? So
yes, sir. Yes,
I'll
sir.
give a 5-minute break, and then I'll just continue
Yes,
again. Okay.
So, dear all, we will be joining back in 5 minutes.
Yeah. After that, I'll discuss this mobility. So
Yes.
derivation of how mobility expression comes. Was that done earlier?
No, sir. No, sir.
So
Expression
I'll do
for was not. Yes.
it. Yeah. So I'll do it.
But ma'am, but Aaron, she has to take one more session. He's not lifting the problem.
Yes, ma'am. Hi. After this session, do you have another session? Okay, after sir completes, you will be having. You'll be taking. Okay, and in that also please give 5 minutes break. You have to change the dress. Okay, thank you. Good session.
So let us resume.
Yes, sir, please.
Yeah. So my screen is visible, isn't? So now let us discuss mobility. How the expression for mobility comes about. Yeah. So suppose there is so let us first look at the electron movement in silicon. So in silicon, electrons have a random thermal movement. So how does that look like? That suppose there is this electron here, it would move till this point, and then there is a collision event or scattering event. Then it goes somewhere else. And again another scattering event and it goes here. Another scattering event and it goes here. Another scattering event here. Like that. So now if you apply an electric field, how would this movement change? Since you have applied
सिस्टम
this electric
ये
field,
इनपुट जो है
the
ये इनपुट
electron
कौन
would
सा
slide.
इनपुट है
Now this thermal velocity between
वो
the
जो बोल रहा है
scattering
वही है
events, thermal velocity
हाँ ये वो ले रहा है
is of the order
वो जो बोल रहा है
of
वही ले रहा है
10 to the
तो
power
सिस्टम का
7
वॉल्यूम कम करने से फर्क नहीं पड़ेगा
centimeter per second. It's very large.
एक ये वाली लाइट भी जलती है साथ साथ एक्स्ट्रा बॉडी वाली भी
So now
एक्स्ट्रा
you
बॉडी
बट अब ये कल तो
suppose you apply
बट
this
अभी
electric,
ठीक है चल रहा है अपना
अभी तो
this
ठीक है
part could change a little, but nevertheless this is
इसके
just
बाद
a.
मैम का एक
I
सेशन
mean,
मैम यहाँ से लेगी
since it's random
वो तो घर से ले रहा है
behavior, you cannot
ये
be
ज़्यादा better है,
deterministic
मुझे
like
पता है।
this.
सही में
But I'm
better है,
just
ज़्यादा
trying
better है।
9
to
o'clock रख दिया
paint a
मैम
picture. So this would
डेली
कभी भी
slightly
होगा तो खुद
get
के
altered.
घर से
हाँ,
आए तो हम भी
फिर
अपने घर से
हम
बैठ
इधर
सकते
इधर
हैं
not get altered, not
हाँ,
मतलब
इधर
एक
बैठ
से
जाए
लैपटॉप
not
लैपटॉप
not
नहीं
getting
करते
altered.
जरूरी नहीं है यही सारे करें
This
सही।
would
मैम
अब
आई
मैम यहाँ आएगी तो हमको आने पड़ेगा चल रहा है
orders of magnitude. So you can assume as if the valence band electron distribution is not affected at all.
बट मैम का सेशन भी है इसके बाद
So it's thermal like this. It would slightly get up. So if we look at an ensemble of electrons, for all the electrons, this would actually get altered. So if you look at all the electrons, it would seem as if all of them have the same random motion.
बीच बीच में
And on
ब्रेक
that,
मैम बोला वही लेंगे
a
बीच में
slight
स्पीकर आज
motion in this direction has been added.
टेबल पे था बट
Okay.
yesterday में
So
दो
with
सेशन
VTH,
बनाया
there
थर्ड नहीं
is a
बनाया
small
नहीं
movement
नहीं आप सेमीकंडक्टर
in this
करें ना
direction which has been
हाँ,
added to
बट
all
अभी
the
चेंज नहीं कर
it
पाएंगे
would
ना
seem like that.
नहीं हमने ऑलरेडी बनाया है इसके कल बनाया था
कितना?
शाम को
Is that
एक तो
So,
बनाया था सुबह 9 से 9 बजे
as if the random
बनाया था
motion
10
is
से 12
staying
एक
as
बनाया था
it
12 से 1
हाँ,
शाम वाला
and
नहीं
the
बनाया
ensemble of
ओके
electrons,
शाम
all the
को
electrons
हाँ,
are
सेशन
moving,
3 में फिर उसी में ज्वाइन करेंगे
वो भी कर
moving
लेंगे
in the direction
सेशन अभी
opposite to
ज्वाइन
the
करना
the
तो
third.
सेशन 3 है
ठीक
Yeah,
है
electric
शाम
field
को
कराओ।
में बनाएंगे
So,
वो शाम वाला बनाना है वो
I
ओपन
think,
फ्री
if
इसलिए
you
कितना
look
बजेगा
like
तो
all
बनाना
the random
इसके
motion
बाद
has
मैम का
been
तुरंत है
to the random motion
आप 5 मिनट का टाइम लगेगा ऑलरेडी बना
some
होगा
small
हाँ,
हमसे
use करेंगे।
वो यूज कर लेंगे
movement in the direction opposite to the electric field is added. So the random motion and scattering stays similar to what it was before the electric field was introduced. So when the electric field was zero, there was random motion of electrons and current was zero. When you apply electric field, the movement due to the electric field is superimposed on the random motion. The random motion stays as it is. Is that fine? So that's a very important thing to be understood. So as Professor Karbandkar says, it's like structures. So it is as if you have a tray of sweets on the road. So this road thelawalas, this kind of. So he will have tray of sweets, and on that bees are hovering. So these bees have a random motion. So when he moves the cart, he's selling sweets on a cart. When he moves the cart, the random motion of the bees remains the same, and of the flies, the random motion of the flies, it remains the same, and they move along with the cart. So that is as if the electrons have retained their random motion, and they are moving along a direction opposite to that of the electric field, keeping their random motion intact and their scattering intact. So the scattering doesn't change for small electric fields. So that's all. So here, random scattering is unaffected due to electric field. For small values of electric field, it's not affected. Okay, so so now we can also see, but so right. Let us now use this idea to develop the concept of mobility. First, let us see that what would be happening. Let us guess when you have a constant or steady state current. Okay. If you have a steady state current I, and you have this block of silicon through which this current I is flowing, now you have a cross section here on this block. So if there is steady state current, then there are these electrons here. Suppose they move with a velocity v. Suppose they move with a velocity. In 1 second, the electron here would have moved to a distance v within 1 second. Okay, it would have moved to a distance v within 1 second, and this v within 1 second. So what is and the carrier concentration is suppose n. So what is the current that would be flowing? We would say that the current is, what is the number of electrons that have gone now? Carrier concentration per centimeter cube is n. Okay, and suppose this has an area, this block has an area A. So, and how many, and what is the length that these electrons on an average have covered? V. The length covered is V, area is A, so A into V into carrier concentration, that is the number of electrons that have crossed this cross sectional plane 1 second. And what is the charge of each electron? Q. So therefore this velocity is A into N, and A is area, into N into Q into V. And if therefore density, current density is NQV. Okay. So what you observe is that in steady state, when there is constant current, V, the average electron velocity V must be constant. Okay, so here V must be constant. So that is one for steady state constant current, DC current, as you call it. So that is the case. Now let us start looking at what would happen to the electron density if we so electron momentum. Okay, momentum of the ensemble of electrons, that is collection of electrons. Suppose you are looking at electrons within a certain volume. So you are looking at electrons in this volume, which is suppose 1 centimeter unit volume. So these electrons, what is the net momentum that they would gain? You would say that suppose the electric field applied is this, and this is the x direction. So you would say that dp by dx, which is the rate, the gain of momentum in rate with which the dp by dt, rate at which the the momentum of electrons is increased, is if there are n number of electrons, then it is n into q into electric field. So if electric field's direction is this, then the momentum gain is in the negative direction, in the opposite direction. So whatever is the electric field, in the opposite direction, momentum is gained, because these are electrons. This seems to suggest that the electrons would keep on gaining energy. Okay, and they would with time, they would keep on gaining energy linearly with time for a uniform electric field. But we are seeing that for constant DC current, this drift velocity or velocity of electrons must not change, must remain constant. How is this possible? So that is because of scattering. So what we find is that the energy that is gained by the electron because of the electric field like this is lost in the scattering events. By the electrons in due to electric field is lost due to scattering. So what do you mean by this? So the energy gained is lost when the electrons encounter the lattice atoms or lattice. Okay? So it is given to lattice as heat. So, or momentum gain, loss due to scattering. So, that's why you have a constant current, a constant velocity. See, for constant current, you also require a constant velocity, drift velocity. That's what we had observed. And what is this drift velocity? It is the for the ensemble of electrons, that is collection of electrons in this unit volume, the uh, a velocity has been superimposed on the random motion. So whatever has been superimposed on the random motion, that is what we are calling drift velocity. It's an average kind of velocity of all the electrons within that small volume, okay, within this block. So this drift velocity is average velocity of the electrons in the ensemble of electrons. This is the average velocity within the ensemble of electrons. So what? So in this unit volume, the collection of electrons is the average velocity. The random motion of all the electrons when it is taken together comes sums up to a zero. So it's only this superimposed drift velocity on the random motion, which when you add all the momenta together, random motion results in a zero momentum. So the momentum is only because of this drift velocity. Now let us see what happens because of the electric field. Suppose initially in this block there are just at time t equal to 0, initially, suppose there are n naught electrons within this unit volume which have not undergone scattering. That is, initially we are looking at time 0. You are saying that all the electrons are where they are. I want to see when they would each one of them would undergo a scattering event. So you begin counting scattering events. Okay, so you begin counting scattering events. So suppose, so all these electrons are alive. All these electrons are alive within the ensemble or within that unit volume. So you will see that each one of them has the same probability of scattering. They're randomly placed in the entire unit volume. So each one of them has an equal probability of getting scattered. There is an average probability of getting scattered. Probability that an electron would encounter would undergo a scattering event within unit time. Let us call that probability as 1 by some Ts scattering and as 1 by T bar. So this T bar is not time, it's an so it is a probability. 1 by T bar is a probability. So what do you mean by this? Let us think. So it is the probability that an electron would undergo a scattering event within a unit time. Okay. So for how long does an electron not undergo a scattering event on an average? Or within a time dt, delta t, what is the probability that an electron would undergo scattering event? So that probability is delta t into p scattering. This is probability that an electron would undergo a scattering event within a unit time. In delta t, the probability that it would undergo scattering event is delta t into p scattering. So that is delta t by t bar, isn't it? So what is the so in time t bar, what is the probability that an electron would scatter? It is 1. It is 1, isn't it? Would undergo scattering. So in time t bar, an average electron would undergo scattering. So therefore, this time t bar is called mean free time. Okay. Therefore, this is called mean free time. So time t bar is therefore mean free time. So what do you mean by this? So it is the average. It's an average or time within which an electron would undergo a scattering event. Okay. Now, why are we doing this? We were saying that the energy, the momentum gained due to electric field, this cannot be indefinitely being kept gained. So it is balanced by the momentum lost due to scattering events. Otherwise, you could not have had a constant drift velocity and therefore a steady state or a constant DC current. So now let us look at the momentum that is lost because of scattering events. Then these two momenta, when you add them up, should lead to a zero. And that will give us a way of introducing the concept of mobility. Yeah. time t is equal to 0, we were saying n naught, we are considering n naught electrons. At time t is equal to t, or at time t, let us say that n electrons have still not undergone scattering. That case, what is the momentum? That is, so now this momentum is of the ensemble of all the electrons within that unit volume. Okay, so what is the momentum which is lost because of scattering events? So we are saying that in time dt, the probability that an electron would undergo a scattering event is dt by t bar, that we are seeing. Probability that an electron would undergo scattering event. So if there are n electrons, what is the probability, what is the rate at which they would undergo scattering events? If there are n electrons which have still at time t, which have still not undergone scattering event, so what is the time, what is the rate at which they would undergo scattering event? That would be n into dt by t bar. Rate so this is the rate of scattering of electrons at time t. Okay. Now this is the rate. So if on an average they have a certain velocity, average drift velocity or something, then the so that and average mass it has, so then you can say that you can just the rate at which momentum is lost is then mass into some drift velocity into n. This is now the total momentum. Whatever is there because of the random motion is cancelled because it's random in nature, so they would, all the components would get cancelled to dt by t bar. What is this? This is now this is the rate of loss of momentum at time t due to scattering. So dp by dt see, this is the probability at which an electron would undergo scattering within time dt. And this is the rate of scattering of electrons at time t, because n electrons within the volume, unit volume, have not undergone scattering event at time till time t. Okay. So and rate at which electrons would encounter scattering at time within the not rate, so number of electrons which would encounter scattering within that time dt would be this probability into number of electrons which had not undergone scattering. So this is the number of electrons which would undergo scattering. So now if I multiply electron mass and the drift velocity, so random motion doesn't contribute to overall momentum of the ensemble, because all the electrons are randomly moving and components would get cancelled and the momentum would be zero because of random movement. But because of the electric field, now there is a momentum. So how much is that? N into this. So what I am saying is, but within this, how many N will be lost? That is given by this. So this much momentum would be, so the loss would be this much. How much of N would be lost? N into dt by t bar. So how much of the momentum would be lost? Whatever was the momentum into dt by t bar. So this is loss of momentum. So that is dpx. Okay, this is dpx. So dpx, therefore we can write that dpx by dt is equal to mn star vd this entire thing is px, isn't it? So therefore we can write, this is the momentum of n electrons. So therefore we can write this as px by t bar. So dpx by dt is therefore px by t bar. So that is, and this is a loss. So therefore this is negative here, negative sign is there. Okay, so now this is because of momentum loss due to scattering. So what is the now the total momentum? So the momentum is actually changed. It is remaining constant, isn't it? So it means that because of electric field and because of scattering, the change in momentum dpx by dt due to electric field and dpx by dt due to scattering should add to 0. So what is dpx by dt due to electric field? It is this. So minus n q ex, okay, minus px by t bar should result in a 0. So what does that mean? Now let us write down this. Minus nqex minus mn star effective mass of electrons into drift velocity into the electron concentration within unit volume, which is n, divided by t bar. That should result in a 0. So what does that mean? That means that drift velocity Vd is actually minus, so this n would cancel, isn't it? N on both the sides cancels. So you would have the drift velocity Vd or the average, and so it's an average. That's why we are of the entire ensemble of all the electrons in that unit volume. It's an average. That's why we are putting in this braces, angular braces. So that comes out to be minus q p bar by mn star into electric field. So this is what we are calling as momentum. Okay? And that's why you write this expression that this is actually momentum So now let us see what happens if there are scattering due to various reasons. Suppose there is scattering because of this lattice scattering, there is suppose phonon scattering, suppose there is scattering because of dopant ions, so there is scattering due to silicon atoms, scattering due to dopant ions. Both are different because silicon atoms would in general be neutral and the dopant ions are positively charged, so the scattering would be different because of both of them. So suppose there is a probability of scattering with silicon which is 1 by, suppose the probability of scattering with silicon atoms in the lattice, suppose it is 1 by T bar silicon, like that we write. And then probability of scattering with dopant ions, suppose it is 1 by T bar dopant. Now, these two probabilities would add. Total probability of scattering would be 1 by T bar silicon plus 1 by T bar dopant, isn't it? So what would be the result on mobility? So now mobility is, or you are saying that mobility is this, isn't it? Means that since the probabilities add like this and mobility is proportional to reciprocal of the probability, you find that final mobility should be 1 by mobility due to silicon scattering and plus 1 by mobility due to dopant scattering, like that. Whatever are the components of scattering, for each of them, if you have the mobilities separately, then all these mobilities would add as reciprocals because of this reason. That the probability that mobility, as we see here, is actually proportional to the probability as a reciprocal. Probability of scattering events happening as a reciprocal. Anything you want to ask or discuss here?
Hello?
Yeah. Anything you want to ask or discuss here?
Sir, there is no question so far. If there is some question, I will let you know.
So how long should I continue now?
Sir, maybe 10 minutes. Is it fine with you?
Yeah, sure.
Oh, okay.
So, yeah. So this was not done earlier, is it?
Yes, sir. You are covering in detail. I have not covered that in that much of detail.
Yeah. So then how current density is obtained from this mobilities, that you might have covered. Un plus
Yeah, yes, sir. Yes.
n mu n plus p mu p. All
Yes,
that
sir.
you might
That
have covered, is it?
yes.
Resistance,
That I covered.
that you have covered, is it? So I will then cover carrier lifetime. That might not have been done, is it? Carrier lifetime and how
Yes, sir.
that might not have been done. I think I'll be able to do that within this time, 10 minutes, okay? Recombination of carriers. So first let us look at direct recombination. So if you have this valence band and conduction band, electrons and holes, suppose they directly recombine. Okay? So in a EK diagram, you will have it like these holes are here, electrons are here, they would directly recombine. K represents momentum, E represents energy. So just don't worry about this. This is this you need not worry about. If this was not done in the course, don't worry about it. Just look at this picture. Just look at this picture. So this direct recombination. So what would be the rate of recombination? So if I want to understand the rate of recombination, then suppose you have excess carriers. Why how excess carriers would be produced? Suppose you have a block of silicon on which you are shining light. If because of at a constant rate, constant intensity and a single wavelength. So you have suppose the wavelength is such that the photon energy is larger than each. In that case, you would be exciting electrons. Okay, so that would produce more electrons. Electrons are excited. Into conduction band from valence band. Okay, So now electrons are excited into conduction band from the valence band, but there is, suppose this is a p-type semiconductor. The p-type semiconductor block. So these electrons would find lot of holes here. These excited electrons. So, and these are separated in energy state, but actually they are all in the same location physically. No, physically they are all in the same location. So what would happen? Now they would get, so they would be recombined. So if now there are more electrons in the conduction band because of the excitation, the generation rate has increased. Okay, but if there are now more electrons in the conduction band, they would also the recombination rate would also increase, because there are more electrons here, and the probability that an electron would recombine with holes remains the same. The hole concentration is not changing much, because suppose hole concentration is 10 to the power 16 per centimeter cube, and rate of excitation would produce say 10 to the power 30. If 10 to the power 16 per centimeter cube electrons were there, then holes are there, then without the light, the steady state electron concentration would be of the order of 10 to the power 4 per centimeter. But suppose you have excited electrons, and therefore the electron concentration is now 10 to the power 12 per centimeter. It is orders of magnitude smaller than that of the hole concentration. So this is called low level injection or excitation. So the minority, in this case electron concentration, is increased, but N is still much smaller than P, even after increase. Okay, so this is low level injection. So in low level injection, you can assume that the whole concentration is not changed at all due to the electron concentration. So the probability that an electron would recombine with holes remains the same. It doesn't change. So when you are increasing probability of an electron recombining with a hole remains constant. Okay. So so when you are increasing the electron concentration by this exciting light, the probability also, since this probability remains the same, the rate of electron recombination with holes also increases. So soon, therefore, now more electrons are getting excited, more recombination is also happening. So soon recombination takes over and becomes equal to the generation. So soon generation becomes equal to recombination, and a steady state is obtained. Okay. So once this is done, once the steady state is obtained, then after that, suppose you put off the light. You put off the light. Okay. Light source. So now once you have put off the light, then again now you want to see what is the rate of recombination. After you put off the light, what is the rate of generation? as we had seen, it is proportional to Ni square. Let us call that proportionality constant as alpha r. That is now a function of temperature T. That's all. We had seen that in the previous hour. Okay. So what is the rate of recombination then? What is the rate of recombination? Rate of recombination we had seen is the same proportionality alpha r into whatever is the electron concentration into whatever is the hole concentration. Okay? And we want to see how this N of T, P of T change. And now, since there are more electrons than the steady state and light has been put off, if light has been put off, it should come back to the original equilibrium condition, where finally N should be equal to Ni square by P and P should be nearly equal to dopant density. So that steady state would again come back. How does it come back? That's what we are trying to find. So, so now generation is not equal to recombination because generation is this and N of T is now much larger than what it is. N of T is much larger than Ni square by P naught, or okay. So therefore, you would find that the recombination rate is now higher than the generation rate. That's because you have just now put off the light at T equal to 0. At T equal to 0, you have just now put off the light. And the excited electrons are still present in the conduction band. So N of T is larger than P of, much larger than this value, the steady state value, Ni square by P. So now I would want to get the rate of recombination, rate of reduction of N of T, dN of T by dt. How much is that? That would be now rate of generation minus rate of recombination. With rate of generation, electrons are generated in the conduction band, and with rate of recombination, they get recombined to the valence band from the conduction band. Okay. So what is this? This is alpha r Ni square minus alpha r N of T P of T. Okay. So this also can be written as where delta N of T, you can define it as N of T minus N naught, where N naught is Ni square by P naught, the steady state values. Okay. So since this steady state value is a constant, delta, rate of change of delta N of T is equal to rate of change of N of T. So now let us solve this. What is this? Alpha r Ni square minus alpha r. What is N of T? N naught plus delta N of T. What is P of T? P naught plus delta P of T. So you can just write it as alpha r Ni square minus alpha r N naught P naught minus alpha r n naught plus p naught into delta n of t
Hello, sir.
minus alpha r delta n of t delta p of t. Now here we observe that the change in electron concentration should be balanced by change in hole concentration, isn't it? Why? Because how is the electrons concentration being increased by light? It is exciting electrons from valence band to conduction. So it means that many holes are also produced due to charge neutrality. Delta n of t is equal to delta p of t, or electrons are excited from valence band to conduction band. That is how delta n of t and delta p of t are resulting. So therefore both of them are equal. So that's why I am equating both these here. Okay, and that's how I am getting this expression. So finally, what do I observe? I observe that d delta n of t by dt is equal to, now what is this? N naught P naught? N naught P naught, this is Ni square. So therefore, these two terms would get cancelled. Likewise, what is this? Delta n of t and delta p of t. This is low level injection that we are speaking about. Delta n of t equal to delta p of t is much smaller than p naught. That's why it is low level injection. So in that case, this delta n of t into delta p of t would be much smaller than this alpha r into n naught into p naught plus p naught into delta n of t. So this is much, n naught plus p naught or p naught is much larger than this delta n of t. So therefore, you can neglect this term. This term you can therefore neglect. So what finally results is just minus alpha r n naught plus p naught. Of this also, you know that n naught is much smaller than n naught is n naught you have written here is much smaller than p naught. Is it? Ni square by p naught is much smaller than p naught. So therefore, you can again neglect this here. So this delta n of t, so you get an expression d delta n of t by dt is equal to minus alpha r p naught. Okay. So, so what does that mean? It means that delta n of t is means that delta n of t is equal to is proportional to exponential minus t by tau, where tau is alpha r p naught. Okay, so so what is this minus t by tau? So it means that the rate at which n of t decays is proportional to so the decay is now an exponential function like this. So what does this mean? That if there are delta n of t excess electrons, they would decay with a function that is, so this you can also rewrite as delta n of t divided by tau. Isn't? You can rewrite this, or you could have rewritten the earlier expression again as d delta n of t by dt is equal to delta n of t divided by tau. Okay. So what does this mean? If there was an electron and its probability that it would recombine in a unit time is 1 by tau, probability of recombination of the electron in a unit time. So if 1 by t is the probability of the recombination of the electron in a unit time. Yeah.
Excuse me, sir. How much time it can
I
take?
am just finishing in 1 minute. If
Oh,
1
thank you so much.
1 by tau is the probability of recombination of the electron in a unit time, then for delta n of t electrons, the rate of recombination would be delta n of t divided by tau. Is it? So that is what this entire discussion leads to. So this is called tau is therefore called carrier lifetime. Okay. Yeah. So here I stop. Anything you want to discuss, you can discuss now.
So, participants, if you have any question, please type in the chat box. So, I think there is no question so far, sir.
Yeah.
So, thank you so much, sir, for the really enlightening session. I hope all the researchers and the faculty members will utilize whatever you have taught them in a good manner to prepare for their research